Hello everyone, today we will be finishing up our discussion of normal curves with an overview of random variables. Now, random variables are really just variables that are left up to chance. So, for instance, if you toss a coin 100 times, the number of heads that you get really is left up to chance. And the reality is the mean here that we would expect is for it to be 50 heads, 50 tails. But when you toss a coin 100 times, you're not going to have it be exactly 50 heads and 50 tails every time you do that. There's going to be a distribution of how many heads you get, and that distribution actually follows an approximately normal curve. So, related to this concept, there's two principles that we'll discuss. So there's the honest coin principle, and then there's the dishonest coin principle. The difference in when we use these is whether or not the probability of the event that we're dealing with is 50% or if it's something else. So the honest coin principle is what we'd use for something like an actual coin toss where the probability of heads or tails is exactly half and half. So in this case, if n is the number of coin tosses that we are doing in one trial, so say we're doing this in sets of 100 coin tosses, n equals 100, then our mean for the number of heads is just going to be n over 2. So in this case, that would be 100 over 2 or 50. So kind of what we would expect. The mean number of heads we're going to get is going to be 50 out of 100. Our standard deviation is going to be the square root of n over 2. So this would be the square root of 100 divided by 2, which gives us 5. So the honest coin and dishonest coin principles tend to work best when we have larger numbers of coin tosses involved. So usually 30 or more is a good guideline. Now, this next brings us to the concept of the standard error. So the standard error is basically just the standard deviation expressed as a percentage of the sample size. So in this case, the total number of coin tosses. So the way we would express that is 5 as a percentage of 100, which would be, if we express this as a decimal, that would be 0.05 or 5%. So we would say we have a standard error of 5%. Now, let's say that we increase our sample size to 5,000. So we're doing trials of 5,000 coin tosses, and we're going to see out of those 5,000 times how many heads do we get. So mu, once again, that's n over 2, so 5,000 over 2, or 2,500. Sigma, square root of n over 2, so square root of 5,000 over 2, which gives us 35.355. So our standard error, once again, is just going to be our standard deviation as a percentage of our sample size, which is 5,000. Which gives us, in decimal form, 0.00707 or 0.707%. So this is the honest coin principle. So the honest coin principle, once again, applies when whatever event that we're dealing with, in this case coin tosses, is something that has a probability of exactly 1/2. When the probability of whatever event we're dealing with is not 1/2, so say it's 0.7 for instance, This would be like saying if you have a coin that when you flip it, it has a 0.7%, or sorry, it has a 70% chance of landing on heads and a 30% chance of landing on tails. For this, we would use the dishonest coin principle. The formulas for the mean and standard deviation are shown right here on the board. So mu equals np, and sigma equals the square root of np times 1 minus p. So for this scenario, if we are doing 100 coin tosses per trial, mu would just be n, or 100 times 0.7. So 100 times 0.7 is going to give us 70. And then sigma is going to be square root of 100 times 0.7 times 0.3. So 0.3 being 1 minus p in this case. So this would give us 4.583 as our standard deviation. And then the standard error is just going to be our standard deviation as a percentage of our sample size. So in this case, that would be 0.04583 or 4.583%. Next, let's say that we increase our sample size to 5,000 again. So mu, we have 5,000 times 0.7, which gives us 3,500. Sigma is going to be square root of 5,000 times 0.7 times 0.3, which gives us 32.404. And then our standard error, once again, we take this 32.404 and express it as a percentage of our 5,000. Which gives us a standard error of 0.00648 or 0.648%. So as you can see in both cases with the honest coin and dishonest coin principle, our standard error decreases whenever we increase our sample size from 100 to 5,000. So this brings us to the concept of the 95% and 99.7% confidence intervals. So the 95% confidence interval we'll just do for our dishonest coin with 100. So the 95% confidence interval is basically just going to be our mean plus or minus, or two standard errors on either side of our mean, basically. So our mean in this case is 70 out of 100, that would be 70%, plus or minus 2 times our standard error, so 2 times 4.583%. So what this would give us is 70% plus or minus 9.165%. (99.7% confidence interval, we're going to do the exact same thing, except that we're going to do plus or minus 3 times our standard error. Which in this case would be 13.748%. So that means that basically when we toss a coin 100 times, there is a 95% chance that 70% plus or minus 9.165% will land on heads, with our dishonest coin for P equals 0.7. And then for 99.7%, that would be 70% plus or minus 13.748%. Thank you for watching, and as always, I'm happy to help with whatever questions you have.